Good morning, Astronomy 1020. Welcome to our sixth lecture in this fall 2020 semester. In an ideal world, we would be taking this week to move on and actually address our first astronomical image, the sun. But as Huey Lewis says, ain't no living in a perfect world. I think there's some things that we need to do to finish up our chapter on light, radiation, and telescopes. So what's probably going to happen today, short of a miracle, is I'm probably going to go over some concepts like the Stefan Boltzmann Law in a little more detail. I'll talk to you guys about angular resolution and the diffraction limit, some more abstract properties of light. And then just clean up a bunch of scraps, and at the end of it, we're going to have a lab. Hello, Devin. Hey, what's your pooch's name? I like that guy. Or is that a cat? I can't even tell what that is.
It's a cat. His name's Moose.
Hey, Moose. I'm glad he's going to be chilling out here to learn about light.
Oh, yeah.
Maybe we can even talk about the eyes of cats and how they're related to our lecture today. And then for our lab, we're going to learn how to build a simple basic telescope, a Keplerian reflector. If you have time during the lecture, you should print out this sheet. This is a data sheet. You can also use you can also edit the PDF directly, but this data sheet here, let me go to speaker view and click on me. It has boxes for measuring the focal length of lenses. There's some stuff on the back that we might use. You could maybe copy this, but I'm not sure if we'll get to it or not. But definitely this page here, which is 8-5. Okay, cool. So let's start off by thinking about light bulbs. Here's a light bulb. Inside is a tiny piece of metal, which makes up the filament of the bulb. That's what actually produces the light. You can see it in there. I don't suppose any of you guys know what that metal is made out of. It's a particular type of metal that they make these light bulb filaments out of. I was just, curious if
Is it
know. Sorry, Devin?
Is it copper?
Not copper, actually. The wires are certainly copper, but once it gets to the little filament that glows itself, they transition to a different metal.
Isn't it magnesium?
No. Okay. I'll tell you, it's called tungsten. It's a special metal in the periodic table. They refer to the filaments in these light bulbs as tungsten filaments. And I'd like to show you why. I've got a periodic table of the elements here, but we might need a more advanced one. Tungsten is element number 74, 16. And it has the symbol W, because in German it's called Wolfram. The reason why they use the element tungsten is because it has one of the highest melting points of any metal on the periodic table, besides maybe iridium, which is very, very rare. Let's look up a periodic table of the elements. I like the Sergeant Welsh one. I used to use this one when I was in a chemistry class a long time ago. If we could find a high resolution one, that would be lovely. That's not high resolution enough. One of these will certainly be. There we go. 3,000 pixels sounds good. Okay. I want you guys to check out this periodic table of the elements, which we may want to look at in detail from time to time. If I zoom in here, you'll notice in the legend that they have all kinds of intense information about the element, including shown in blue, the density, and shown in black, the melting and the boiling points in Kelvin. You'll notice that tungsten, where are we here? Element 74 has a melting point of of 3,700 Kelvin and a vaporization point of 5,800 Kelvin. That means tungsten could almost survive as a metal at the surface of the sun, which is pretty wild to think about. Now, as you guys know from our discussions of the elements, each element in the periodic table has a unique emission line spectrum. And if I go back to my periodic table of the elements, slide 16, sorry. You'll remember that I showed you guys a periodic table of the elements where instead of showing you the symbol of the element, I'm instead showing you what their emission line spectra looks like. Now let's count to see where tungsten is. 1, 2, 3, 4, 5, 6 down. 1, 2, 3, 4, 5, 6 over. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And this one right here, let's get out my annotate. This is the emission line spectrum of tungsten. You'll notice it shows many more lines than hydrogen. It shows some blue, purple lines, some green lines, a couple of orange lines. And yet, when we looked at the tungsten filament with our spectroscope during our spectroscopy lab, what did we see when we looked at the spectrum of a light bulb, of an incandescent bulb? Do you guys remember what we saw when we looked at the spectrum of an incandescent bulb? I need to hide the trolls here. The trolls are bothering me. There we go. No one? I figured you'd have your notebooks right there with all those emission line spectra that we took in last week's lab. So you have to be able to remember things for me to teach you new things. If you can't remember anything, then I just kind of have to repeat the same lecture 15 times. Cameron, I cannot hear you, but I would like to hear you. Nothing? Hey, Christopher Leonard, at the end of lecture today, I think I was missing one of your assignments, which is very unusual because you almost always turn in your assignments. I can't see you either, Cameron, if that makes a difference. So Chris Leonard, we should talk about that. I wonder if I have, do I have it? I think I threw mine out. Oh, hey, look, Cameron knows. Yeah, okay, Devin, what do you see? Cameron knows what's up. He said a continuous spectrum. That's right, buddy. When we took the tungsten filament and broke apart its light, we saw this, a smooth, continuous rainbow. So I guess the question I'm trying to ask the class is, what's up with that? Why did a heated up piece of tungsten, which should have a unique emission spectrum that looks like this, why did it produce a pure rainbow for me when I looked at it through my spectroscope in my lab? Could anyone hazard a guess? Maybe it's got something to do with Kirchhoff's laws of radiation. Why don't you guys look up Kirchhoff's laws of radiation? What produces a continuous spectrum? Come on, someone play with me. Okay, yes, Cameron, a blackbody, but we need more than that. I need to know why tungsten will sometimes produce a rainbow and why sometimes it will produce an emission line spectrum. And how do I know when to expect which spectrum? Yes, Cameron. Geez, Cameron, I wish you were not a troll today because you seem to have some good ideas. You're sort of on fire, aren't you? So Cameron's suggesting that maybe the secret is it's got something to do with a solid versus a gas. Could one of you read off Kirchhoff's law of black bodies for me? That would be cool. All you got to do is just read what I put down on the board.
A hot, dense, glowing thing produces white light.
Produces a continuous spectrum.
Yeah.
And I put white light in parentheses. So Cameron's saying it's the dense part. It's hot and it's dense. Somehow when it's dense, the type of radiation it produces no longer depends upon the chemical element, but only on one property, and that's the temperature. Let's take some notes on this. Speaker view. Okay. So, a tungsten filament bulb produces a continuous spectrum, not an emission line. If we were to ask why, it's because it's a hot, dense solid. And when it's a hot, dense solid, it basically acts like a black body. So Cameron helped us get there. I thought that we could use our newfound Stefan Boltzmann and Wean's law to kind of understand what the radiation profile of a tungsten filament bulb looks like. I can't remember if we did this last time. My memory is that we ran out of time right at the end of class. So let's draw a picture of a tungsten filament bulb, okay? And it's shining out some very whitish light in all directions. And the filament has a temperature of 3,500 Kelvin. Now, these are the kind of questions I'm going to be asking you on the test which is 2 weeks from today. Y'all processing that? See, up to now, you've just been kind of riding along on my coach and buggy, just doing whatever I write on the board. But 2 weeks from now, you're going to have to do something on your own. And that's probably going to be scary for you guys, right? All right, so let's think about that. So I'm going to ask you 2 questions here, and you're going to do your best to answer them. Question 1 is, how much light does it emit? And question 2 is, what is the peak wavelength emitted by the bulb? As far as I know, guys, we didn't try this sample problem last time. But I did give you the formulas. It's up to you guys to tell me which formula will answer the question, how much light does this black body emit? So hunt through your notes there and find a formula for me. Could someone please interact with me? Anything? Devin, what do you got? Not Wean's law, Gianna. It's not the Boltzmann law, Cameron, but the Stefan Boltzmann law. What does the Stefan Boltzmann law say? The Stefan Boltzmann law tells us that the brightness of a black body is equal to sigma times temperature to the fourth. Where sigma is the Stefan Boltzmann constant. 6 times 10 to the minus 8. The units are watts per square meter per Kelvin to the fourth, multiplied by the temperature, 3,500 Kelvin. Okay, last time I taught you how to do this, so do it. Tell me what the answer is. While I sip some coffee. You guys are punching, right? Caroline, I know you're punching. Oh, shame on you. You know, you have to fight extra hard for your education in these unprecedented times. So talk to me, buddy. Talk to me, Caroline. Yeah, don't slack. No slacking. Nicely done, Jesse. Nice to hear from the trolls occasionally. But Jesse, I don't like your moves because that's too many sig figs and your number is clearly greater than 1 million and it's not in scientific notation. So clean up your answer if you want me to accept it. I want that in scientific notation, 2 sig figs. What you got, Emily?
Where do I find the button on the calculator to do it to the fourth again?
That button, let me use my Logitech autofocus here. And let me go to speaker view. That button is right here. It's x to the power of y. That's good, Jesse. 2 times to the power of 4 is 16. Jesse, I need some units for that too. I'm going to keep pestering you. Jesse, I want units. I want units. Where did I put that bulb? What are my units? It's too bright. Get my focus back in order here. That's a small diffraction grating. You can see that you're getting very pure rainbows when I use my spectroscope there. I wonder if I could hold the spectroscope up to the camera. That would be pretty tight. This might take a little bit of extra. Oh yeah, look. Look how pure that rainbow is right there. That's cool, huh? Wow, I've got some tricks in my sleeve today. Okay, so what are the units, Jessie? Jessie's got 9 million for her answer. What are the units? Come on, guys, this shouldn't be, oh yeah, sorry. Riordan says watts per square meter, and she's correct. Okay, now I've got a thought question to ask the class. I assert to you that the temperature of this bulb is 3,500 Kelvin, just like we had in our problem. But when I look at the wattage of my bulb, you guys can see it's only 60 watts. How can a 60-watt light bulb produce 9 million watts per square meter? Can anyone answer that riddle? See, it seems like if you plug this in, you get 9 million watts per square meter. 9 million watts sounds like a lot of luminosity. How can a 60-watt bulb be also producing 9 million watts per square meter? Can anyone answer the riddle to that?
Is it because of the surface area of the filament?
Listen to that. Christopher, you impress me, Sirrah. Christopher understands the difference between brightness and luminosity. If the luminosity is 60 watts, but the brightness is 9 million watts per square meter, it must mean that that little coil of metal that's in there has such a tiny little surface area. It's so much less than 1 square meter that it only radiates 60 watts. Like if imagine Christopher taking, oh, there's Austin. It's about time we see your face. It's imagine taking a hammer and smashing that metal down into a little surface, probably the size of your pinky fingernail. On the other hand, Christopher, as he already understands, if this chunk of metal was 1 square meter, which is basically the size of this board, if I had a piece of metal, a sheet of metal the size of this board, 1 square meter, and I heated it up to 3,500 Kelvin, it would give off 9 million watts of luminosity. That would probably be enough light to burn the hair right off my skull. Okay, nicely done. Now, before we answer the second question, which is what is the peak wavelength emitted by the bulb, I want you guys to take a moment to think about the rainbow for a second. I need to erase this. Any objections? I need to talk to you guys, and this is a very important point before we go on with our next lectures. I need to talk to you about what's called a Blackbody spectrum profile. And since you're in a science class, one of the things that we're trying to learn how to do is get comfortable with graphical information. So I want you guys to make a graph here. Let's make one axis the brightness of light, and the other axis would be the wavelength of light. So this is the brightness in watts per square meter, and this is the wavelength in nanometers. Do you guys remember the range for the visible spectrum? What wavelengths in nanometers does the visible spectrum span? What's the wavelength of purple light? What's the wavelength of red light? I expect you to memorize these numbers.
Is it 400 nanometers to 700 nanometers?
Very good, Chris. I like your moves. Chris, what comes just after 700 nanometers? What regime of the electromagnetic spectrum? What comes after
Infrared.
red? Yeah, infrared. Very good. What comes before violet?
UV.
And then we have X-rays and gamma rays and radio. Actually, do you guys want to know a cute little mnemonic device that might help you on the test? A mnemonic device to remember the order of the electromagnetic spectrum. I call it YXUver. Gamma ray, X-ray, UV, infrared. It's kind of cute because you have UV and infrared spelled out right in your mnemonic device. So my nickname is YXUver, and that will help you remember the order of the electromagnetic spectrum. Gamma ray, X-ray, ultraviolet, visible, infrared, radio. You couldn't ask for a better mnemonic device. So the question I have is this. When I produce this white light, and I'm going to try to do this once again for the class here. The question I'm asking in this graph, I want to plot brightness as a function of wavelength or color. Now, part of the issue is that you guys are going to be looking at it through the CCD camera, which doesn't necessarily display the colors with the same profile that your eye would do. But I'm going to sort of show you the, come on, baby, I can do this. Does it look to you like all the colors have equal brightness? Or does it look to you like some of the colors are brighter than others? What would you guys suggest?
Looks like red, green, and blue are the brightest.
Yeah, I guess it does kind of look like that in your CCD, doesn't it? Well, okay, but what would the graph look like? Let's ask this. Let me try this a different way. Do you know what the graph would look like if all the colors had the same brightness or intensity? What would the graph look like? So this is VibGyor over here. What would the graph look like if every color had the exact same brightness?
Straight line?
Yeah, that's right. I needed to make sure you could see that. If all the colors produced the same intensity for a black body, it would be a straight line. It turns out that you can actually go about measuring this. What you do is you take some type of photosensitive light meter and you scan along the rainbow, measuring the brightness at each color. And what you discover is nature does not produce all colors with the same brightness. Nature produces some colors brighter than others. And when you plot that graph, this is what the graph looks like. It's known as a black body spectrum profile. And it looks kind of like a bell curve, except that it's not symmetrical. It's got a wider tail at the long end. This function depends upon the temperature. But I'd like you guys to note a few points about it. The first thing is you're actually getting emission at all wavelengths of the electromagnetic spectrum. So let's take that as a first note up here. A black body produces all wavelengths of the EM spectrum. Sometimes people abbreviate the electromagnetic spectrum as the EM spectrum. A black body produces all wavelengths of the electromagnetic spectrum. But the second issue is that not all wavelengths are emitted equally. There is one wavelength, which I call lambda max. It always emits one wavelength more than any other. And this wavelength, lambda max, this is what is described by Wean's law. It is sometimes called the Wean Peak. The Wean Peak is the highest wavelength emitted by your blackbody. You'll notice that in the slideshow, I've shown a slightly more advanced version of this formula here, or of this graph here. Notice that the Wean Peak changes with temperature, going from infrared to red to yellow to green to blue as the temperature goes up. Also notice that the whole graph overall increases, so all wavelengths are emitted greater as the temperature goes up. That's the Stefan Boltzmann Law part of things. Okay, do you guys have this? Austin, are you still writing? You're good? Okay, I'm going to erase this. So let's answer question 2. What wavelength is greatest?
Bless you.
Thank you. For a temperature of 3,500 Kelvin. Wean's law tells us that the peak wavelength of emission is 3 million nanometer kelvins divided by the temperature. So your job is to plug in the temperature. That should be easy enough. What do you get? Don't leave me hanging here.
Uh, 860 nanometers.
Nice. Okay, now here's how I'm going to follow this up during the exam. Once you've calculated 860 nanometers, what regime of the electromagnetic spectrum does that peak in? In what regime is this wavelength found? Yes, Cameron, infrared. So I guess what I'm saying is this light bulb here, this light bulb does not even peak in the visible portion of the spectrum, which is hard to believe because you can see its visible light here. This light bulb is actually giving out more infrared radiation than any other wavelength. No shit, I can actually feel that infrared light. When I put my hand up close to this bulb, I can feel, you know that warmth that you feel? That spooky action at a distance warmth? That's not conduction, that's radiation. You're feeling infrared radiation. It's basically acting like a toaster oven does. It's toasting the skin on your hand with infrared radiation. Man, what a stupid fucking waste of energy these things are. You're like paying Narragansett Electric, you're supporting Al Qaeda or whatever the hell by wasting all of this energy, right? And most of it's actually not even going into the visible where you intended it to. Most of that energy is being pumped out in the infrared. By the way, if you did have to answer that question, what color would this actually be producing more than any other? This actually does produce one visible light color more than any other. Can you guess what it is? Yes, Kaitlyn, red. And Kaitlyn knows that because if you look at the graph, you can see that when you peak here in the infrared, forgive my Stroop test colors here, that you're actually giving out more red light here than you are violet or blue light over here. Now, when you mix all these colors together, they do look kind of whitish, but I suppose now that we know that, I guess this bulb, it does kind of have a rosy red glow to it. You know, it's kind of similar to the white light that you get from a candle. It's kind of warm and reddish. You know, this is one of the reasons why your skin looks better under incandescent bulbs than it does under those hideous blue, I don't have them in here, thankfully, but those, yeah, mood lighting. That's right. And what mood lighting is it actually applies a natural blur or a natural makeup to your skin. So check this out. So let's say we could look up close at your nose, like with a microscopic magnifying glass or something, right? Your nose, which normally you think looks like this, actually kind of looks a little bit more like this, right? Okay, and what's happening is when you bounce blue or green light off of it, the much shorter wavelengths of blue light, they can scatter off those tiny crags and reflect all the imperfections on your skin. But longer wavelength red light is less sensitive to those bumps. And so it tends to sort of naturally smooth out your skin when you look at it under red light, because it hides all those microscopic blemishes and imperfections. So if you're going to have a romantic dinner, you much prefer candlelight or even incandescent light than you would to fluorescent tube light, which has mostly green light from the emission lines of mercury. This is what's so cool about LED lighting. An LED light bulb actually does not use blackbody radiation to produce its light. It uses the process of emission lines by taking atoms and stimulating their electrons and getting them to emit red and blue and green emission lines and then mixing them together. But because of that, if you were to look at the spectrum of an LED light bulb, it basically would look like a box. It wouldn't give off any ultraviolet. It gives off roughly equal amounts, or they can change the amount of red, blue, and green, and then it gives off no infrared. So basically, the reason why a 100-watt light bulb that's incandescent is equivalent to like a 30-watt light bulb that's LED is because if you have a 100-watt incandescent light bulb, most of those 60 watts are being pumped into this area of the spectrum, heating up your house, whereas only about 30 watts of energy make it into the visible spectrum. So the LED lights just cut out all of that unnecessary infrared light, and they produce the light at wavelengths where your eyeballs can see it. They save you money, they're good for the environment, all kinds of things. So LED light bulbs are the best. And nowadays, they can actually mix the levels of red, blue, and green so that they are still pleasing and pleasant to look at. Other problems that we could try. What about me? Am I not a hot, dense solid? Should I not glow? What about the temperature of a human being, right? Could we consider ourselves to be black bodies? Let's find out. Let's try one more problem, okay? So here, is a 99 degree Fahrenheit or 310 Kelvin blackbody. And this person, in theory, should be glowing at some, yeah, exactly. This person should be glowing at some wavelength. So let's ask the same two questions once again. How much light am I emitting? And question 2 will be, what is my peak wavelength? All right, you guys know the drill. Which formula answers question 1?
The Stefan Boltzmann one.
Okay, so let's apply it. The brightness is 6 times 10 to the minus 8. The units are watts per meter squared per Kelvin to the 4th times the temperature, 310 Kelvin to the 4th power. It occurs to me that some of you might have had trouble in the last problem punching this in. And I, usually I like to see if you guys can do it, but then for the people who aren't picking up on it, I like to show them. Let me get my calculator and I'm going to punch this one in with you here, just to make sure that y'all getting it, especially for the people back home in the night class, okay? 6 exp -8 times 310 raised to the power of 4 equals. What is my brightness? Students? 2 sig figs.
550.
550 what? Yeah. Okay, so I have a brightness of 550 watts per meter squared. This is going to sound, well, Halloween's coming, friends. Something tells me it's going to be a bit of a bummer of a Halloween because we can't go out to Halloween parties without catching COVID. But in the spirit of the Necronomicon, the ancient book of the dead, bound in human flesh, do you think a human being has a square meter of skin on their body? Like, if I have a brightness of 550 watts per square meter, I want to know if I actually have a luminosity of 500 watts. So if you flayed a man and you stretched his skin across this whiteboard, kind of like they did in the Necronomicon there, do you think you've got enough skin on your body to cover this?
I would say yes.
I think the human body does have very close to a square meter of skin. I think I even read something like the average person, because you've got all these weird folds in your body and stuff, So I think it's close to almost 2 square meters of skin. But here's the thing. You want to know what bothered me about this calculation for a long time? Is we cannot actually have a luminosity of 550 watts. And the reason why I know this is because I know what the typical calorie requirement of a human being is. We have a power requirement of about 2,500 calories per day. And if I wanted, I can convert that into watts. It's calories to joules. I'm going to do this one pretty quick. A food calorie is 4,200 joules. And what are the number of seconds in a day? Who's seen Rent and knows? There's 86,400 seconds in a day, I think. 60 squared times 24. Yeah. So there's 86,400 seconds in a day. And if you do this, you get about 120 watts or 120 joules per second. I probably did that fast. You guys are going to have to think about that later, okay? The thing that really messed me up is I know a human being has 1 to 2 square meters of skin, so they should have a luminosity of about 500 watts. But here's the problem. If you are only eating 120 watts, you have to output 120 watts. Otherwise, the conservation of energy would fail. I cannot generate energy from inside my body. I am not a nuclear fusion reactor, nor can I destroy energy from the universe. So if I'm eating 120 watts of cheeseburgers, I've got to be pumping out 120 watts worth of radiation. How am I supposed to figure out this riddle? It took me 2 years to do it because I'm slow sometimes. Do you guys think you can beat me? Can anyone guess why I'm not actually pumping out 550 watts despite putting in the temperature of a human being? It's not about the surface area. The surface area checks out. It's about variations in temperature. 310 Kelvin is 99 degrees Fahrenheit. The temperature of your skin is not the same temperature as your internal organs. Let me show you. I have an infrared image of a man taken by NASA. I really love this picture here. Let's see if I can find it. Oops. Bear with me here. Here we go. Slide 86. This is a thermal infrared image of a man, which is color-coded to show intensity of infrared radiation. Where does the man give off the greatest amount of infrared light?
His head.
Yeah. I guess the brain is a very energy-intensive organ. We do need to keep that warm. But look as you go towards the extremities, the amount of infrared radiation the man's giving off drops. Your fingertips are not at the same temperature as your core. Oops. We'll get back to that in a moment. You know, there are other organisms that have adapted their eyeballs to see creatures at infrared radiation. Most famously, since I spoiled the picture already, the pit viper. Now, the pit viper has a normal set of eyeballs. We can talk about the slit in a little bit. And these eyes are like most organisms. They see at visible wavelengths from 400 to 700 nanometers. But these things here, they look like nostrils, but they're actually a secondary set of eyeballs called the L'Oreal pits that are unique to pit vipers. And these L'Oreal pits are basically low-resolution infrared detectors. Little mice and little gerbils or whatever the hell's crawling around the jungle there, these things also glow. Oh, I guess we should talk about the peak wavelength. I'm screwing this up here, guys. So we did the brightness, but we're supposed to calculate the peak wavelength of a man. And as you might be able to guess, it's going to come out in the infrared. Sorry, I meant to, I'm just, you know, I'm not doing this right today. So the peak wavelength, lambda max, is 3 million nanometer kelvins divided by 310 Kelvin, and you get about 9,900 nanometers, or about 9.9 microns. Anything that radiates with a wavelength of micrometers is always in the infrared. So your body is glowing. It's just glowing at infrared wavelengths. And hopefully you don't ever find yourself in a dark room with a pit viper. The pit viper will be able to see you glowing like a little incandescent light bulb. And they will be able to bite your ankles because they'll be able to see you in the dark, okay? It actually starts to make you wonder, why didn't more organisms do what the pit viper did. I mean, here our eyeballs are sensitive to a range from 400 to 700 nanometers, but it might have been helpful if we could see little creepy crawlies in the dark. Why don't we have infrared vision?
Our diet, we like pit vipers are carnivores, but we're like omnivores. Some things are herbivores.
That's
So
actually not a
temperature
bad.
doesn't matter for that.
That's probably definitely related to it, Christopher. That's definitely one way to look at it. Although keep in mind, Christopher, not every carnivore on Earth has infrared vision. I'm sure coyotes and jackals would have benefited from that as well, right? I think the answer probably lies closer to this picture here, Christopher, which is known as the transmission of Earth's atmosphere. The atmosphere of planet Earth is not uniformly transparent to all different wavelengths of the electromagnetic spectrum. The air we breathe is mostly opaque to gamma rays and X-rays and UV. It lets a teeny bit of infrared through and it lets some radio waves through, but there's this narrow window of transparency from 400 to 700 nanometers. That's how you and I can see each other through this fog of gas here, right? It's transparent to visible light. I think some animals don't have as much color discrimination as us, or at least I've heard that, but I don't know enough to know if it's true. Actually, the eyes of many animals are adapted not to see fine detail or fine resolution, but to detect movement. And that's related to another property of light called diffraction. And I need to get to that in a little bit. But for now, the concept that I wanted you guys to think about was our eyes, one of the reasons they've adapted to see the visible spectrum of light is these are the wavelengths of light that our atmosphere is transparent to. And this is one of the reasons why ground-based astronomy is usually only a visible telescope or radio telescopes. But when astronomers want to look at other wavelengths of the electromagnetic spectrum, they actually have to send the telescopes into outer space to get away from our atmosphere. Our atmosphere is a nuisance to astronomers, despite the fact that it keeps us alive. Okay. I've got two more modules I want to do with you today before I burn through this entire lecture. I want to talk about discriminating fine detail and how tiny an angle can an eyeball or can a telescope see. First, let me start by revisiting something called the small angle formula. We use these two formulas in our homework on Thursday, but I don't feel like I had enough time to discuss them. So a problem that we have in astronomy very often is of a pair of binary stars. Okay, so let's consider a pair of binary stars. And sometimes you can see the two binaries separate from one another. That's called a resolved binary. Sometimes the binaries appear so close together in the sky that they kind of merge into a single dot. That's an unresolved binary. And in a way, the binary stars are kind of code for any two fine details. Like, for instance, if you look at this ruler stick here, in order to be able to discriminate, okay, so I need to do my focus here because my focus on the lens is not really set up for near field. In order to be able to discriminate two fine tick marks of this ruler, each of those little ticks is kind of like a little binary star. You're seeing a tick over here and a tick over there, and you need to have enough separation for them to be able to resolve as individual ticks. You'll notice that as I bring the ruler further and further away from the screen, the tick marks no longer look individual, but they kind of blur into a fuzz of gray. Can you see that? At this distance, your tick marks are unresolved, but somewhere about there, you can start to resolve the individual ticks. Can you guys see that? This is actually in every way identical to the problem of binary stars. Remember that you see angles, you do not see distances, okay? Now, when we first learned the small angle formula, it was in chapter 2. And let's draw the picture here. So here are two binary stars or two diddly bobs or two fuzzies on a sweater. They could really be any two little wacky little doodads you're trying to resolve, okay? And they're separated by a distance s. S is the separation. You're looking at them from over here, some distance away. In chapter 2, you learned this version of the small angle formula. Well, we could write it in one of two different ways. S is equal to theta times d times 2 pi over 360. That's when you want to solve for the separation. Or if you wanted to solve for the angle, 360 degrees over 2 pi times the separation divided by the distance. And this is what I call the small angle formula part 1. Because in this version, theta is measured in degrees. However, students, when you're trying to separate two very tiny little things, like these two tiny little tick marks, degrees are not really the best angle for us to use. And that's why I'm about to introduce a new version called the small angle formula part 2, where instead of measuring the angle in degrees, we're now going to call the angle alpha. And I'm just going to call it alpha to remind myself that it's now going to be in arc seconds. Which from henceforward on in this class, it will be much better to measure angles in arc seconds, because we're going to look at increasingly further distances where we need very tiny details. It turns out that if you take 360 degrees over 2 pi and you do a conversion from arc seconds to degrees, 1 degree is 3,600 arc seconds, you get this kind of magical number in astronomy, 206,265 arc seconds. So I can rewrite the small angle formula part 2 in the following two ways. S is equal to alpha times d divided by 206,265 arc seconds. Or if I want to solve for angular size, the angular size is 206,265 arc seconds times the separation divided by the distance. Take a moment to get all that down because it's kind of important. It's definitely going to be important on your exam, where I will give you several questions related to this formula. I think we should try a sample problem so you guys can understand how it's used. Does everyone agree? Devin does anyways. I'm just going to take a minute here to let you guys finish writing these notes. Kaitlyn, are you good? Does anyone object to me erasing? All right. Let me give you guys a practical example of how you might use that. Wait, oh shit. I'm sorry, Cameron. Cameron, I didn't see that. That's one of the things about being a troll is it's kind of hard to hear from you. You guys have a delay, okay? All right, Cameron, either watch the video later or check out the class notes. Okay, I want to tell you guys about a binary star that I like to show friends when I take them out to the telescope. The name of the binary star is called Albireo. And Albireo is a binary star that's in the constellation Cygnus. So the constellation Cygnus is also called the Northern Cross. And let's see if I can walk you through this. The star Cygnus is one of the brightest stars in your sky. It's up at night right now. If you go outside at nighttime, you get 1, 2, 3 stars in a cross. And then if you go down here, there's kind of an ordinary brightness star. You can clearly see the star even from downtown Providence, but it looks kind of faint and it doesn't look too fancy, okay? Let's talk about what happens. It looks like a single star to your eyeballs, but here's what happens when you sort of look at this star through a telescope. It resolves itself into a beautiful, oh wow, here's the constellation Cygnus. This star up here, Deneb, is much brighter than the others. So Albireo, Cygnus is a swan, and Albireo is sometimes called the eye of the swan. This is what happens if you look at it through a telescope. You see a beautiful yellow and blue star. In fact, we can do it better than this. I'd say a more true to life version of what you see when you look through your telescope is kind of something like that. So you see these two beautiful stars, one is blue and one is yellow. I believe these two stars are separated by 35 arc seconds, and their distance away, if I can remember this, what's their damn distance? 430 light years. And let's make sure they're separated by, yeah, separated by 35 seconds of arc. So let's try this as a sample problem. And let me explain what I want us to do, okay? So for starters, let's consider the binary star known as Albireo. The angular separation is about 35 arc seconds, and the distance is 430 light years away. Here's the question we want to answer. Find the separation in astronomical units, and let's ask ourselves, are they bound by gravity? Sometimes binary stars merely appear as binary stars. For instance, here's, let's do the right colors for Albireo. Here's a blue star and here's an orange star. These two stars could be what's called an optical double. In an optical double, the two stars are actually very far apart from each other. They only appear close because they're sort of close together in angle, and one is closer than the other. Another possibility is that the two binaries are actually close to one another, right? They're not an optical double, but they're actually bound by gravity. Now, I'm going to make a weak argument and say our solar system is like 100 astronomical units in diameter. So if they're 1 to 300 AU apart, then I can consider them bound by gravity. But if they're thousands of astronomical units apart, then I will be suspicious that they are bound by gravity. So let's find the separation in AU. First question I want to ask is, Which formula should I use?
Small angle formula.
Part 1 or part 2?
Part 2.
Yes. Do I want the one that solves for S or the one that solves for alpha?
Solves for S. So
Correct. Because S is the actual separation. Good. Wait, there's one more issue though, Kaitlyn. S is alpha times D 206,265 arc seconds. If I plug in arc seconds there, that cancels. So the units of D and the units of S will be the same. I can either plug in light years in the beginning, get light years in the end, and then convert it, or I can convert light years to AU and then plug it in. Either option is totally okay. Which one do you prefer?
are you asking me?
Sure. Since you made the mistake of talking to me, I'm asking you.
Okay. All right, we'll put light years in first.
All right, screw it. So let's try that. So let's do 35 arc seconds times 430 light years over 206,265 arc seconds. What do you get? Two sig figs. Any Kaitlyn, sure, or anyone?
Oh yeah, okay, I did get the right thing. 0.07.
That's one sig fig.
72.
Round better.
Oh, 7.3.
That's right. So you've got a tiny ass number of light years, but that doesn't tell you much because light years are huge. We want to convert this to astronomical units. How do I do that? Kaitlyn, why don't you give it a shot?
You have to do like the X bar thing, right?
Yep. Could you do that with me?
Sure.
All right. So there's the X bar. Give me
Put
units.
LY on the bottom.
Uh-huh.
Is it AU on the top?
I don't think you have a conversion from AU to light years.
Yeah, you're right.
So you'll have to go from light years to what? Look at your formula sheet. This is what you're going to have to do on the exam, and I won't be there to hold everyone's hand. So let's look at, do you guys have that formula sheet that I gave you last time? So what you do is you go to your formula sheet and you look for your conversion factors. What do you have light years into?
9.5 times 10 to the 12 km.
Right. So I guess we'll do kms on top. What's going to be in your next division bar?
KM on the bottom, AU on the top.
Okay, now give me all the numbers.
Can you go back to that page for me?
Sure can. This is just how you'll do it on the test.
Thank you, sir. So on the first one on top, you're gonna put 9.5 times 10 to the 12 km.
Yep,
And then on the bottom is gonna be 1.
correct.
And then the next one is gonna be 1 on top.
Yep,
And then 150 times 10 to the 6 km on bottom.
nice. And that's exactly how we're going to be doing things on our exam, okay? All right, so punch them up and tell me what you get. My focus looks wacky. I gotta check my focus. Ooh. I tried to turn off my auto white balance. I look as red as a tomato. Okay. What is this? Weird. That looks normal. Okay.
Is it 4.6 times 10 to the 15th AU? Oh,
No.
wow. Maybe
No
not.
way. Maybe Cameron.
Wait.
No, neither. No one's gotten it right yet, guys. That's, you just multiply and divide and use your EXP key. I don't know if I like this color balance thing. I feel like I'm purple. Well, okay, but tell me, Emily, tell me how to round it. I'm tired of looking at your calculators. I want to hear an answer. I need to know that you guys can round off appropriately. Emily, it looked like you had the right answer. Can't you round that for me?
I'm trying to figure it out, but I'm not exactly sure what I'd round it to.
2 sig figs. Keep the first two numbers and get rid of everything else.
So 4,600.
That's what I want to hear. What are the units?
AU.
Good. What do we think about those two binary stars? What do you think? They're actually closer than Alpha Centauri is to the sun. What do you think? Do you think they're bound or they're not bound? Come on, someone play with me here. Do you understand what I mean?
Are they bound?
Maybe just barely. They're certainly a lot farther apart. It's actually, people debate it, but I think the answer is yes. If they are bound by a very, very long period orbit. Look at this. It is not known whether the two components, beta Cygni A and beta Cygni B, are orbiting each other in a physical binary system, or if they are merely a so-called optical double. If they are in a physical binary, their orbital period is 100,000 years. So most people suspect, no, they're not actually bound, because 5,000 light years is kind of a lot. But do you want to know what the real funny thing about Albireo is? Here's the real funny thing of Albireo. One of the stars, do you see the yellow one? It is itself another binary. But you can't see that binary here, can you? Why can't I see that binary for the yellow star?
Too small of an angle?
That's exactly what I wanted to hear. The angular separation between them is too small. Actually, Kaitlyn, it's only about a half an arc second. So the Hubble Space Telescope might be able to see them, because Hubble in theory should be able to get down to half an arc second. This leads to a very funny joke in astronomy. Okay, so every time I say very funny joke in astronomy, you should realize that you're not going to be laughing. okay? And the joke goes like this. Three out of every 2 stars is a binary. And Alberio sums this up perfectly. What looks like 2 stars in your telescope is actually 3. Not only that, students, but when you look at a field of stars, roughly 50% of all stars that you see are unresolved binaries. You know, you think that binaries are like maybe rare because twins on Earth are rare. But in outer space, twins are common. I was fortunate enough to have these 2 very nice twins that took my class a couple of summers ago. And they were really funny and adorable and great students, and I loved teaching them. And one day after class, this is before like all the social distancing, I talked to them about being twins because I was curious, like, what's it like being a twin? What's the etiquette of being a twin? All this. And you know what they told me? They told me something funny. They said, we like being twins. We think it's really awesome having a built-in buddy. And we feel bad for you guys. You know what we call you guys? We call you singletons. So I thought that was pretty wonderful. So now I like to distinguish between singletons, individual field stars, and binary stars. In nature, binaries are quite common. Now, later on in a different class, I will tell you how we know that that single star is a binary. It's some other tricks having to do with spectroscopy. But for now, I've got just enough time to cover one last module. And the module that I want to address that's related to all of this is what determines the limit of how tiny an angle you can see. It's a property of light known as diffraction, and it's very complex. So I'm not going to be able to do a great job at making you feel good about this, but I'm going to give you some salient points, and I do have a jazzy demo before we end, okay? So let's start with some notes here. Let's talk about diffraction, or actually, let's start by asking this question. What determines how tiny an angle my optical system could be an eyeball, or it could be a telescope or a camera. What determines how tiny an optical system, what determines how tiny an angle my optical system can see? The answer to this question is a property of light called diffraction. And diffraction could be summed up like this. It is the bending of a wave, and not only light undergoes diffraction, but water waves and sound waves do as well. It's the bending of a wave as it passes through an opening. And the fancy term for opening is aperture. Of size d. So in other words, and there's another issue here. It causes a type of distortion, and that distortion is known as a diffraction pattern. It's so important to the study of optics that this book on optics here by Hecht, a legendary classic, actually shows you a diffraction pattern right here on the cover of the book. So let me slow walk you through diffraction, and then I'll tell you the new formula that you've got to learn. In my slideshow, I have a sort of cartoon picture of diffraction shown by watching water waves pass through a wall. Slide 44. Imagine that you were out in the bay and you watched a large oil tanker come by with some planar waves coming off of its edge. This is the long waves coming off of a boat. If those waves were to hit a seawall and pass through a small opening, you would notice that the waves would bunch up, and as they pass through the tiny opening, they would become circularized. For this to happen, it's important that the diameter of the opening, this big here, is similar to the wavelength of the waves here. And here's the difference of what happens. If you have a small opening, an opening that's comparable to the wavelength of the waves, you get a lot of diffraction and a lot of bending. If the opening of the seawall is large, most of the waves pass through unmolested, but you get a little bit of bending, a little bit of diffraction at the edge of your waves. Every time light or every time sound waves or water waves pass around an obstruction, they bend a little bit and they get distorted. And the distortions can overlap with each other in complicated ways. This, for instance, shows you an image made by a small star as it passes through a small pinhole camera. You'll notice that most of the light from the star is smeared out and blurred out onto this central disk called the airy disk. This disk is itself a bit of a diffraction pattern. It's the smeared out light of the star, but that some of the light of the star ends up kind of contained in these secondary bands. We call them constructive maxima. Some of the light ends up there, some of the light ends up there, but light is missing here and here. It's kind of weird. Let me show you a few more diffraction patterns here. This is light made by passing a laser beam through a slit, and I think I'd like to show you this through a demo here. So here in my hands, I have a cool laser pointer. It's super, super bright. So it actually, I have a dimmer one here. Let me see. This laser won't hurt the camera as much. Now, when I take this laser and I shine it onto my whiteboard, the size of the spot that you see is not a microscopic dot. Okay, Devin, we'll see you later, buddy. But you guys can see that your dot is actually already kind of smeared out on the board, and that's already due to diffraction. Now, I want to show you something interesting. Bear with me, guys. I have a small opaque screen here, but hold on a second. Man, I am running out of time here. Shoot. Oh, here it is. I put this in an unusual spot to protect it, and I couldn't find it. So what you see here is an opaque screen, and this opaque screen has like a number of slots cut into it. Can you guys see that? Now, what you would naively think is if I shined my laser beam through one of these spots, you'd expect the laser just to kind of appear on the other side of the board there whenever the laser is in front of the slot, just as a single dot. But I want you to watch what happens. I'll try to hold this steady when I pass the laser through this slot here. Okay, hold on. I'm going to stabilize the laser here. I'm going to hold this. Can you guys see that? I'm going to try to bring this. Oh, I don't have enough hands to do this experiment right. I'm going to try to bring my focus up a little bit. And I'm going to bring my camera closer, a lot closer. Can you guys see that? Can you see that there's not one dot, but that there's a whole bunch of dots? It works better if I stand back here. Ooh. Can you guys see that?
Yes.
Can you see the individual dots? It's interesting that just passing light through this little hole there, I just shined a laser in my eyes twice, and that really sucked. So when I go blind, I want you guys to know I did it for science. I did it for you. Okay? Anyways. I don't have a lot of time to talk about diffraction because I'm kind of out of time, but diffraction distorts light and it messes up your ability to discriminate two objects. And if I can show you one more slide from my slideshow, the idea is here. Diffraction not only causes these fringes around stars, but it also smears the light of the star out into these disks. And these disks aren't the actual image of the star. They're the smeared out light from the star due to diffraction. So in other words, the wavelength of light and the size of your telescope determine how big these disks are. These disks are an artifact of photography. They're not related to the size of the star at all. When they blur together, the two stars disappear and their diffraction patterns overlap. And basically it works like this. There is a limit known as the diffraction limit, which is the minimum angle your telescope or eyeball can resolve. Which I'm going to call alpha minimum. The diffraction limit is the tiniest angle you can resolve at wavelength specified by lambda and telescope diameter capital D. And the formula goes alpha min is 250,000 arc seconds times wavelength divided by diameter. That's the diffraction limit. It's a very important formula. It tells you how tiny an angle your telescope can resolve. Can I see the supermassive black hole at the center of the galaxy? Can I see the American flag on the moon? Can I resolve all of these tiny dots? This is a two-dimensional diffraction pattern, by the way. So this is all done by putting a diffraction screen on top of my laser. All right. I think I'm going to stop there in the interest of time. We'll try examples of that later on in our class. At this point, we'll take a pause and I'll get ready for our lab on telescope design. Does it sound good to everyone? Okay. 10 minutes, 15 minutes, something like that? Okay, I like it. Hello, everyone. I'm back, and I'm ready to do the lab. Yes. Okay. I took a moment to set up here. It took me a little longer than I wanted. Let me get my Wi-Fi on. Display. Turn off auto lock. Let's see here. So I have everything I need ready to go. And I just need you guys. So does anyone else want to join the party, or are you going to just sit in your beds in your PJs there? The page number, Kaitlyn, is 8-5. Okay, Jesse. So I'd like to see, look at that little guy. Wait, it's so dark, Jesse. What is that? Is that a cat?
It's a bunny.
It's a bunny. I love your bunny. What's your bunny's name?
Serena.
Serena. Wow, jet black. Does your bunny help you do the lab?
Yeah. Well, he eats it.
He eats the lab?
Yeah.
I had a bunny once called Spuds, and Spuds ate every wire in my house. I don't.
He's done that.
Yeah, they love wires. They love to chew through wires.
Mm-hmm.
Cool. All right, it's nice to see that guy. Dog ate your bunny? Austin, that's messed up. I'm calling the SPCA on you, pal. Today we're going to learn how to build a basic telescope, a Keplerian refractor. And we're going to do so with some of these guys here. Let me see if, oh, geez, ouch. Wow. I just totally made a mess. Fuck. Okay. That was not what I wanted to happen. I was just looking for one of these guys. An extra convex lens, okay? We use convex lenses to build basic telescopes. And this convex lens is in every way identical to a magnifying glass, okay? The kind that Sherlock Holmes might use to investigate a clue. All you need to build a basic refracting telescope is 2 of these convex lenses. Notice when I hold it sideways, it kind of has a meniscus shape here. It's kind of fat in the middle and skinny on the edges. So as a preamble to what I'm about to do here, let's show you guys a couple of slides having to do with lenses. I think it's slide 100 maybe. Okay, so lenses work by the law of refraction. This is why we refer to telescopes that use glass lenses as refractors. The idea behind refraction is that a light ray comes in from outside, and when it strikes the glass, it bends towards the normal. That may not sound like a big deal, but if you shape your glass correctly, you can get light to bend in a variety of interesting ways. If you've ever seen a stick appear broken in the water, that's because light travels at a different speed in the water than it does through the air. So when light hits the water-air boundary interface, the change in density causes the light to bend, and it refracts the light, making the stick appear broken. There's all kinds of cute things you can do with the law of refraction. A useful thing would be to build a convex lens. Here's a side view of a convex lens. We shape the lens in the form of a parabola. You'll remember that parabolas were one of our conic sections that Kepler had studied. When you do this, something interesting happens. Light from a distant source, like the moon, will come in and it will strike the lens at a variety of different angles. And it causes all the different rays of light to all bend by a slightly different amount. And this brings all the rays of light to a focus point. If you were ever a little pyromaniac like me, then you know about the focus point. That's where you can take sunlight and bring it to a microscopic dot, and then you can set the woods on fire or whatever, okay? You're bringing light to its focus point. Here's what we're interested in today. The distance from the lens to the so-called focal point of the lens is called the focal length of your lens. So from here to here is the focal length of your lens, and this is what we are going to attempt to measure today. It's the distance from the lens to where it brings all of the light rays to a focus point. It turns out that what you can do is you can put a little index card here or a piece of photographic film. This is what is called the focal plane. And you'll actually make an image of whatever is on the other side of the lens. So if you're looking at the moon with your lens, you can actually make a little image of the moon right there at the focal plane. If you take away the card, the light rays will kind of pass right through. And then you can do something very interesting to build a telescope. Okay, so almost all optical systems in nature use some types of convex or concave lens. Both eyeballs and cameras both use convex lenses, to bring an image to the focal plane. In the case of a camera, it's film. In the case of an eyeball, it's your retina. So let's cut open your eye. Inside you find that there's this little gooey sac called the lens. It's shaped in the form of a convex lens, and it brings rays of light to a focus point on the back wall of your eye. So these rays are brought to a focus point at your retina, and at the retina, the light is converted into an electrochemical signal that goes to your brain, and it tells you what you're looking at, like mint chocolate chip ice cream or something. One of the cool things you'll discover about convex lenses, and you'll find this out today, is that when you make an image with a convex lens, the image that you make is always inverted or upside down. And in a way, that means that everything that you look at in your field of view, you see it upside down. You've just never really thought of it as upside down because it's always seemed right side up. You're gonna have to think about that one for a minute. Okay, anyways, you'll see today that lenses invert things. If we want to build a basic telescope, let's skip ahead through my slides here. A basic telescope is really just a long paper tube with two lenses. The one that gathers the light is called the objective lens, and the one that you put your eyepiece up to is called the eyepiece. Usually, but not always, the objective is both bigger and longer in focal length than the eyepiece. Let's strip away the paper tube for a second. Light comes in through the objective. It's brought to a focus point at the focal length of the objective lens over here. Then you take a second lens called the eyepiece, and you put the eyepiece at just the right distance away, where the distance from the focus point to the lens is the focal length of the eyepiece, f sub I. Then the rays of light will come out of the lens, and they will be parallel once again. Now, you might want to ask yourself, what did this telescope do for me? Parallel rays of light come into the lens. Parallel rays of light come out of the lens. What do you think the purpose of a telescope is, students? What's the function of a telescope? Why do I use telescopes? What am I trying to do with them? Can anyone think of anything useful that a telescope does for you?
Look at things farther away from you.
Okay, Chris, but is it distance that we see, What do we see when we look through our eyes at the world? We don't see distances. I don't see you as 2 meters away. I see you in what form?
Seeing objects then further away. Actual.
But you're not actually changing the distance. What property are you changing? What property do you change when you look at something through a telescope? You make it seem closer, but what you really do is changing what property? Okay, well, hold on. Someone in the chat window has an idea. Well, size is the wrong thing to say, Gianna, because I might think of physical size. I might be 2 meters tall, but you don't see me as 2 meters. How do you see me? Magnification, but what is magnification? All right, guys, I've said it before. I'm going to say it again. You see angles. You don't see near, far. You don't see big, small. You see angles. To magnify something is to change its angular size. And telescopes do this. For instance, notice that here, these two angles, this ray and this ray, might be the angular size of a planet or a moon. And when the rays of light come through my optical system, what started off as this little angle here ends up being a slightly bigger angle over there. I have magnified the image when I've changed its angular size from 0.5 degree to 3 degrees or something like that. But magnification is not always the point of a telescope. In the case of the moon, it surely is nice to magnify things. And that's because when I magnify the moon, I can see more details on it. Now I'm going from an angular size of this big to an angular size of this big, and I can see more features on the moon. Magnification also helps with planets and other things like that. But magnification is not always important when you're looking at galaxies. The Andromeda galaxy, for instance, our sister galaxy. What if I were to tell you that this galaxy, come on. Okay, this lecture depends upon me being able to show you a picture of the Andromeda galaxy. What the hell is going on here? All right, there we go. Shoot. Can I please magnify? All right, let's go to the Wikipedia page. What if I were to tell you that this galaxy, okay, subtends an angle of 3 degrees on your sky? From there to there, the angular separation of Andromeda is 3 degrees. How many times bigger than the full moon is that? Oh, snap. Am I talking to a bunch of students who don't know the angular size of the moon? I didn't think there was anyone in my class who wouldn't know the angular size of the moon. I don't want to talk to people like that. Them peoples are ignorant. I want to talk to enlightened students who know the angular size of the moon. What's the angular size of the moon? What's Mr. Chat Window say here? Half what, Daniel? 0.5 degree. Okay, cool. So I ask again, how many times bigger than the full moon is the Andromeda galaxy?
If it's 0.5 degree, then it'd be, oh goodness. Well, I mean, it's like a difference of 2.5 degrees.
I'm not interested in differences. I'm
Mm.
interested in how many times bigger. 6 times. 3 times 2 is 6, okay? So I don't get it. I can see the full moon with my naked eye. Why can't I see the Andromeda Galaxy? How come you've never noticed the Andromeda Galaxy before if it's 6 times bigger than the full moon?
It's far away, farther away than the moon is to us.
Have you guys heard nothing that I said? You don't see distances, Kaitlyn. You don't see 12 meters away. You see angles. You need another property. It's not distance. Give me another property. It's not about its distance, but it's about its, can anyone guess? Nothing? There's another reason.
Separation.
What?
Separation. It's about its separation.
Its angle is huge. Its angle is 3 degrees. That's a very big angle. It's another property that we discussed in our lectures today. All right. The answer is brightness. You can't see Andromeda because it's dim, not because it's not large enough in angular size. The function of a telescope is not only to make objects magnified in angular size, but also to increase their brightnesses. Notice, for instance, that if your eyeball, let's go to my annotate tools here. If your eyeball is about this big, you can capture maybe 1 or 2 rays per second without the telescope. But if you look through the telescope and you Campbell soup condense all those rays, you can capture 1, 2, 3, 4, 5, 6 rays instead of 1, 2 rays. You're basically increasing the brightness of an object. Those are the 2 functions of a telescope. Okay, now it's time to talk about what we're supposed to do. That was kind of a long-winded discussion here. We don't have a lot of work to do. We're going to attempt to measure the focal lengths of 2 lenses, the objective lens and the eyepiece lens. And once we measure the focal lengths, we're going to put them on a stick and we'll separate them by the sum of their focal lengths. Let's talk about how to do that. I've got a setup here. Here I'm going to have to share with my phone and hope this works. Okay. Darn it. Okay, oops, that's not what I want. Nope. Okay. Come on, baby. Maybe that will help. Okay. Can you guys see this? I have a light source. I have a lens. I actually have 2 lenses. Let's put this one away so we don't get distracted. This lens is called the eyepiece, and this lens is called the objective. I have a ruler here, and I have a screen where I can make an image onto the screen. Let's first go to our lab sheet, okay? So we'll get our name. This is LAB6, okay? And we'll write AS1020. .001 or whatever your section is, okay? Now it says that we're going to be using an orange lens and a blue lens, but I'd like you to change that to objective lens, which will be OBJ, and the eyepiece lens, which will be EYE. We're going to skip this section in the interest of time. But down here, I'm going to change this to OBJ EYE. Okay, so the way the setup works is I've got this optical bench and I've got sort of a light bulb over here. And I've got a piece of cardboard triangle that I'm going to attempt to image the shadow of. You can see the cardboard triangle there, okay? I've done my best to set that cardboard triangle so that it is at 0.0 centimeters. And what I'm going to do is I'm going to push my lens around. This is the lens. And I'm going to push my screen around until I get a sharply focused image of that cardboard. So light from the cardboard will come through the lens. It will be refracted. And then I should get an image of the cardboard, which is magnified and inverted. Let's see if I can do that here. So let's slide this along. Get out of here. Oops, sorry. Now, you know when it's in focus when the cardboard looks sharp and crispy. Here it kind of sucks. My phone is not very high resolution camera, so you'll have to forgive me for it. But there it's out of focus. It's out of focus when the cardboard looks really sharp and crisp, which to my naked eyes is somewhere about there. Can you guys see how sharp the tip of the cardboard is there? Okay. Now, once it's in focus, we have two things to measure. Let us define S as the source distance. That's from the cardboard to the lens in focus. Let us define I as the image distance. That goes from the lens to the screen. I measure S, I measure I, and I can calculate the focal length using the lens maker's formula. The focal length is source times image, get out of here, divided by source plus image in parentheses. You guys got that down? Okay. Let's attempt to measure the focal length a few times for our objective lens. You can see I've got it in focus. Now, we know that this guy is at 0. Tell me if you can measure this. We want to go from the middle of the lens here, right where that number 5 is. What would you say to the nearest 1/10 of a centimeter the position of the lens is at, guys?
Looks like 59.7.
Good. So S would be 59.7 minus 0, or 59.7 centimeters, okay? Now, the image distance is the distance from here to here. So we've got to take that measurement and we have to subtract it from this distance to get the distance in between. So Christopher, what would you say the number 5 is at? Hold on a sec. Let me try to focus this. Ooh. My camera really has trouble with nearby things. Can I add some light to this? I guess not. There we go.
Looks to be at 89.
That means 89.0, right?
Yeah, 89.0.
Okay. But now we have to subtract from 59.7. So have your calculator handy. The interval is 89.0 minus 59.7. 29.3 is your image distance. Okay, we now have to calculate using that lens maker's formula, okay? I'm going to multiply them and I'm going to divide by open parentheses and I'm going to add them. I want you guys to watch my moves here, okay? 59.7 times 29.3 divided by open parentheses 59.7 plus 29.3 close parentheses equals. Round to how many sig figs, students?
3.
So what should I round to?
19.7.
Good. Okay. Let's take another measurement. I'm just going to move this a little bit to defocus it. And now I'll slide the lens a bit until I get it back into focus. Okay, what's my next measurement?
$65.7.
That's not 0.7. That's 65.5. And you're
Oh
done with-
yeah, 65.2.
Okay.
Yeah.
Okay. And now, if you can see this one. Oof. Oh, I hate this. It's because of the lighting there. Let me get a little flashlight or something. What am I going to do here? Hold on. See if you can read that while I find a flashlight. Can you read it?
Looks to be 94.3.
I agree. What would the interval be then? Because this is 94.3 from the cardboard, but we have to subtract here from there to get that distance between the cardboard, between the lens, the screen, right?
29.1 centimeters.
94.3, 60, 29.1. Okay. Can you guys calculate the focal length for me? What you get?
$20.1.
Okay, let's move it one more time. What's our reading?
57.2.
Okay. And the second position?
$87.9.
87.9 minus 57.2 is 30.7. All right. Let's calculate that focal length. 30.7 times 57.2 divided by 30.7 plus 57.2. Close parentheses and then equals. What'd you get? Anyone besides Christopher know how to calculate this? Or is this just like the me and Christopher show? Christopher, you and I make good lab partners.
20.0.
Excellent. Okay, let's take the average of those. Add them up, hit equals, and divide by 3.
.0 again.
I got 19.9. How did you end up with 20.0?
I got 19.9333 and I rounded for you. Sorry.
Right, but that's not proper rounding, right? Because if you're going to chop,
Oh, yep, you're right. I see what I did.
if
Sorry.
you're going to chop there, that number has to be 5 or more to increment it, right? Let's put units on the average, centimeters. Okay, now we're going to swap out and we're going to do this for the eyepiece. All right. And I'd like to sort of show you something. So here's the objective. It's pretty darn thin. The eyepiece is a wee bit thicker than the objective. You'll notice the eyepiece is a bit thicker. That's going to change the focal length. The focal length is now much shorter. So for instance, if I try to make an image, it's so bloody tiny, you probably can't even see it here. My camera can't handle it. So I'm going to take this thing back a bit. And when I bring the whole system in closer towards the light source, I should be able to make a slightly bigger image. Can I actually get that in focus for you guys? Yeah. The image is much smaller than it was before. Let's try taking a measurement this time. What do you guys read?
49.5.
Good.
$63.9.
Not 9. You're going from the
4.
5, Caitlin, not from the 10.
Sorry, 63.4.
Yeah. So we'll do 63.4 minus 49.5, 13.9. Let's calculate the focal length. So we do 49.5 times 13.9 divided by open parentheses 49.5 plus 13.9 close parentheses equals. I got 10.9. Centimeters. Okay, let's move it in a little more. Slide that in. I want to make sure that cardboard is sharp and crispy. It doesn't look like much. I wish the newer iPhones have a much better ability to focus at close things. I need to get a new phone. Okay. What do you read?
$40.7.
$55.5.
So we'll do 55.5 minus 40.7, 14.8. Let's calculate our focal length there. 14.8 times 40.7 divided by 14.8 plus 40.7. Oh, we are precise. We have repeated the same measurement. Remember that precision is when you get multiple trials looking the same. This could be accurate but not precise. This could be precise but not accurate. We'll do one more measurement here. I think that's probably good.
$35.4.
Sure.
$50.9.
Okay. 50.9 minus 35.4 is 15.5. Okay, let's punch them up. 15.5 times 35.4 divided by 15.5 plus 35.4 close equals 10.8. Ooh. Guess what the average of 10.8, 10.9, and 10.9 is going to be? It's going to be 10.866666, which will round to 10.9. At this point, we could stop, but I have another objective to show you. And I don't mean that with a pun intended. There's another method of determining the focal point, and that method is what I call the infinity method. Now, up to now, our source has been this light, and this light has been maybe 30 or 40 centimeters away. That makes it 2 to 3 times as long as our focal length. What if I tried to focus on something a little bit more distant, like maybe whatever's outside the window here? Like these buildings.
Nice view.
I know. It's pretty good. That's why I'm broke all the time. Oh, sorry, hold on. Now listen, I could in theory measure the distance to some of those flying buttresses on the neighboring buildings downtown, and they would not technically be infinitely far away, but they would be tens of thousands of centimeters far away. And that's almost like being at infinity. And something interesting happens when you do that. So let's watch this. What if we take the source, and if we let the source get to bigger and bigger values so that it's almost like it's at infinity? I want you to watch what happens to your focal length here. It's S times I divided by S plus I. And now I'm going to substitute in infinity for S. Infinity times I divided by infinity plus I. Now, infinity plus another number is always basically infinity. Like if my infinity was 10,000 centimeters and I tried to add one of these distances like 10 or 13, it kind of wouldn't matter that much. Infinity plus I is still infinity. Infinity times I is a little scarier because you're multiplying multiple infinities. So I'm going to leave infinity times I alone. And what I notice in my formula is that infinities cancel out, and I get this kind of funky formula. When it's in focus, the image distance, which you'll remember is from the lens to the screen, is equal to the focal length. And I want you to see what that means in practical purposes because it's kind of cool. So first I'm going to unplug. And I'm going to very carefully move this over to that table there. So bear with me. We're going for a little ride here. Oop, I was trying to keep you above the bottom of my pocket here. Let's see if I can do that like so. Not very smooth. I am going to turn the computer because I noticed that if I don't stand in front of the microphone, it gets hard to hear me. And it's probably also good to be able to see through my computer what's going on. That way, if my phone gets too shaky, you can kind of watch what I'm up to here. Oh. Huh. Somebody dropped that at one of my late night carousings this weekend. Okay, so here's my setup. I've got a screen, which I'm going to put kind of far back there. And I've got a lens. But let me get the objective back in here. The objective will work better than the eyepiece. Okay. Think. There's a lot of light coming in from the side of the window, but I want to see if I can get this right. Oh yeah, baby, this is cool. Okay, so let's bring this up. Can you guys see this? What? Can you guys see that? What do you see?
Looks like the dormer on top of the building across the street.
Yeah, that's the old Providence Journal building. Look, you can see all the fine details of the architecture. Let's see if we can see something else. Let's try to look down the street and see if we can see a street scene. I may have to raise this up a bit. It's kind of cool on a bright sunny day. Oh, this is going to be the shit. Hold on. I'm going to try to lower this a bit and raise this up a bit. Can you guys, oops. Can you guys see that? You can see it's a little dim. I have to try to block some of the lights. Let's see what's going on there. You can actually see the top of the Westin Tower there. Can you guys see that? In any case, once it's in focus at infinity, this is the principle behind how a camera obscura works. Let's try to take the measurements. So let's take a measurement here. What do you guys get?
81.3 or 4.
It's 4. It looks a little fuzzy on my phone. Sorry. Well, it's kind of cool. It's a little bent. Let's say it's 81.4 and subtract that from this, from 62.0. What do you get? We're gonna do this part down here, by the way. We'll just do one trial because I'm kind of running out of time.
19.4.
19.4. And let's try it for the eyepiece too. Now the eyepiece will have a much shorter focal length, but the advantage of a shorter focal length, students, is that the brightness of the image will be much greater. They sometimes refer to this as the speed of the film when you're doing photography. Oh, wow. Look how cool that is. I'm trying to see if I can focus mine. There's the focusing of the lens, and then there's the focusing of my camera. So I'm doing a couple of different focuses at the same time here. Can you guys see how bright that is? Maybe I'll just do this nearby building instead. Look how bright that thing is. It's cool. It's like a little projection system. I wish you guys could see it in real life. It's even more dramatic. It looks kind of like shit through the phone. All right, let's do a subtraction here. Give me a number. 81.5 minus 71.1. What do you get?
10.4.
So normally I would do multiple trials with this, but I'm feeling a little lazy today. Let's take the average of 19.4 and 19.9. What do you get if you do that? Do I have to do it? $19.7. Let's put that for our average objective. 19.7 centimeters. And let's average 10.9 and 10.4. $10.7. And now what we want is the sum of the focal lengths. F objective plus F eyepiece. 19.7 plus 10.7 is 30.4. That's how far apart our two lenses should be in our telescope. So let's get out some lens holders. There's one. Oh, here's the other two. And let's get a meter stick. Can you guys hear me okay? Yeah?
Yep. Yep.
So I'll take the eyepiece. Sorry. I'll put it in here. And I'll put the eyepiece at like 20 centimeters. Okay. And now I'll grab the objective. Where should I put the objective if they have to be separated by 30.4 centimeters? Where does this guy go?
50.4.
Yeah, it's got, so they've got to be 10, 20, 30, so 50.4. There. And now, let's see if we've built our working telescope. I'll let you guys look through it. Let me just make a small adjustment. Now it's time to peep on the neighbors. You guys ready? Let's do some peeping on our neighbors. Now this, well, that's not what I meant to do. Shoot. Okay. It's tricky because I'm trying to get my camera right too. Let's take a peek and see if we can see the Weston Tower up here. Okay. Now this isn't the world's greatest telescope, but it works. Can you guys see this image of the top of the tower there? And that's how you build yourself a working telescope. I can check out some people. Notice that everything's upside down. Do you see that? Let's check out. Spy on that fellow who's eating lunch over there. Okay. Let's make sure that you guys have all the stuff you need. Point being, it's possible to build your own telescope with just a couple of lenses. Okay. Have you got all that stuff? By the way, I want to just show you one thing here. The optical design is called a refractor, okay? Now the aperture is the diameter of your objective lens. Here's my objective lens. What does it look like the aperture or the opening is to you guys? What's the diameter of this guy? About 5 centimeters, right? So the aperture of our telescope is 5 centimeters. The focal length is roughly, well, it's close to 20 centimeters, okay? Now, the eyepiece focal length was approximately 10 centimeters, loosey-goosey speaking. Now, the focal ratio is something called your f-stop. In camera technology, they call it the f number, okay? The f number is defined as the focal length of the objective divided by the diameter or aperture. So what would the f-stop or the f number, the focal ratio of this telescope be?
Would it be 4?
Yeah, but Christopher, you write it in a funny way on cameras. You write it as f/4, because 20 divided by 5 is 4. They call this f4 optics. Sometimes the focal length is known as the speed of your camera, because it determines how long you'll have to expose your chip or your photographic film for. The other thing that I wanted to show you, let's skip this, is the resolution and the magnification. You guys remember that you learned a formula for resolution today. It's limited by diffraction. And the minimum angle is 250,000 arc seconds times the wavelength divided by the diameter. The wavelength is optical light, which is around 500 nanometers. The diameter is 5 centimeters, which is 0.05 meters. So if I plug these into this formula, let's check out what I get. This is right from class today. 250,000 arc seconds times the wavelength, 500 nanometers, divided by 0.05 meters or 5 centimeters, 2.5 arc seconds. So that telescope can actually resolve, that crappy little telescope that I just built has a resolution of 2.5 arc seconds. Not too bad. The magnification is the objective focal length divided by the eyepiece focal length. So what magnification am I rocking here, students?
Two.
That's right. It's only a factor of 2 times. And you guys noticed when you looked through the telescope with me, oh, I took the thing off, that it didn't magnify the image very much. So it wasn't a very powerful telescope in terms of magnification. Okay, I just wanted to relate what we did in lecture today a little bit to that telescope that you just built. I kind of went quickly, so forgive me. Have you guys got that? Can you put that on the back of your page? Skip the surface area. I don't care about that. Okay. Let's exit out of this mode here. And that, my friends, is Building Telescopes 101. Nice. Okay, you guys will be sure to turn in these labs ASAP, correct? Don't delay, don't forget. Christopher Leonard, you are always present and a good contributor, so I always take special notice of the students who are contributing well in class. So it scared me a little bit when let me just double check that I'm not going crazy, Christopher. One of your things.
Yeah, no, I know what happened. I think it was Thursday or some Tuesday or Thursday. I had to leave early for a doctor's appointment and I forgot the assignment.
Well, look, I don't want you to get a 0. Wait, I have a 0 for, no, oh, yes, for lab 5. Wait, why do I have a 0 for lab 5, but not for homework 5? Are you sure it was Thursday and not Tuesday?
Yeah, it was Tuesday.
Oh, it's Tuesday. But like, Christopher, you had to leave you didn't do the lab at all? Like, I mean, I'm not just talking to Christopher, I'm talking to everyone. I don't want to see all these damn zeros, you know? I don't want you guys missing stuff. So Christopher, maybe go back and do that lab and send it to me and I'll consider having mercy on you, okay? All right. All right, guys, any other questions? Oh, Emily.
When we're submitting the lab, do you want us to submit the other paper too?
If you don't
The
mind.
one we just did?
The other side, you mean, right?
Yeah.
Yeah, could you do that?
Yeah.
That'll just be 2
Right,
pictures,
thank you.
right, Emily? Okay.
Yeah.
Okay, guys. Well, I had fun with you all, as I always do. Live long and prosper, and I will see you on Thursday, okay?
Thank you.
Bye.
Bye-bye.